Let's get the show on the road. Come on. Yeah, why?
Mom was also, she's like, I was hoping Jason would have posted something good on Facebook this morning. So I think he was on Twitter. He just released all on Wednesday, so he might not have gotten to it yet.
Okay, I'll talk to you later. Okay. Turn the music off. Hide Spotify. Oh, we're recording. I should have paused that. How is everybody this morning? Good. Oh, wait a second. I got to put my video on. Yeah. All right. Good to hear. Everybody have a good weekend? Decent weekend anyway? It was cooler. I like that. Not quite as hot. And today is starting out nice and cool. It was foggy here in Camarillo. Looks like it's cleared up. I hopefully will start getting some fall weather soon. Maybe there might even be rain for Northern California if we're lucky. I thought I saw some people talking about that last week. All right, I'm trying to think. Are there any kind of general announcements we need to make about life, the universe, and everything, and things on campus? I can't really think of anything. Register to vote. Go vote. Help other people vote. Tell people to vote. That's the big thing I can think of. Nothing that I know is happening on campus that I can think of. I can't really think of anything. Anybody have anything they want to share with the group? All right. Not seeing anything. I've got a couple course related announcements to make. Let me get my iPad all ready. Oh boy, where's that? Oh wow. I got the date wrong on my notes. Let me fix that. Yeah. Well, I have to take a second to organize my notes for the day. So let me share my iPad so you can see what I'm writing at the same time, since I'm writing for you. All right, there we go. It's October 5th. This is Calc 1. Oh, yeah. Okay, so just a couple operational announcements for us. I have these things I call grade reports I've made them all. And I just have to email them. And they're customized for each of you. They show the progress you've been making in the class, how many learning targets you've shown me, evidence that you've mastered, and how many learning targets you've attempted to show me but haven't gotten that mastery okay yet. And it also shows you how you've been doing in the context of the way other people have been working. So maybe for some of you, that'll give you a little boost saying, oh, I need to get it going. I need to start catching up. For some of you, it'll be like, oh, yeah, good. I'm doing okay. I don't have a feeling for how fast you ought to be going, but the report will give you an idea of where you are with respect to other people, where you are with respect to the grades, getting grades in the class. We're quite a ways out from the end of the semester, so I don't think anybody should be worried what their score is compared to what the grade is. But this grade report will show you where you are. So as soon as I get some time to email them, which might be this afternoon, you'll see that. So when I send them to you, and when you read them, if you see something in a report that differs from your understanding, oops. You need to talk to me. Okay. And that can be in just an email, or we can have a Zoom chat. But these reports serve two functions for me. One function is I want to let you know where you are in the class, right? It's a way I can give you feedback on how well you're doing in the context of where you want to get in the class. The other function they serve is a way for you to let you know what I know. I'm going to let you know everything I know. And um, if it looks like I have something wrong, I need you to tell me. I want you to tell me so that we can go back and fix it. Either I'm wrong, which is likely the case, or you're mistaken, which is very unlikely. Because you're on top of what you've been doing and what you need to do. I've got emails and information and data shooting between me and 60 other people taking calculus with me right now. So sometimes things can fall through the cracks. And the way I work things, if I make one little typo in a computer program I write to help do grades, that will affect the grades I have for somebody. So it could just be a tiny error. And you can help me find those. And so I can go back and fix them. So we all know that we're clear on where everybody is. So long way for me to say, if you see something wrong in my report, just let me know. It probably means I made a mistake and you can help me fix it. And everybody wins when we do that. Any questions about the reports? They're private reports. I don't share your report with anybody else. I'm sensitive to your maybe not wanting to talk about your grades via email, and that's fine. We can make a Zoom time to chat. All right. So next topic, the learning target quizzes. So, you know that the technology has not been serving us very well. I have, it's been a little bit more complicated than I have appreciated. And last week I finally told people, look, if you want to take a quiz, don't rely on the technology, just email me, ask, and I'll send you a PDF of the quiz. And I had lots of email interactions with students where they sent me a request and I sent them a quiz immediately. Sunday, I took the day off from email. So if you sent me an email yesterday, I probably haven't seen it yet. But I had a breakthrough at the 8:00 class. I worked with somebody before we started class, and I think I fixed the quizzes. So if you've been having difficulty getting the quiz to take a quiz, I think there's good news. And just to let me explain what the good news is. It's my understanding that people were able to get to the Google form to request a quiz. But when they submit the Google form and they'd get the little pop-up that said, oh, you can get the quiz here, and had a URL. It's when they clicked on that URL that they got a message that they needed permission. That has been fixed. I did something this morning. Some students in my 8:00 class confirmed that has been fixed. So I ask you that to try that. See if you can get the learning target quiz you want to take using the normal method. I think the normal method now is normal. It should work normally. But again, if it causes you problems, don't hesitate. Send me an email and I'm happy to email you a PDF of the quiz until I get it fixed. But I think it's fixed now. So I'm going to write that down. Fixed. Okay. So those are the administrative announcements that I want to make. Anybody have any questions about operations?
I actually have a question about the quizzes.
Sure.
Yeah, so it's my understanding that, well, I see here that there are different letters per quiz, and I believe it's my understanding that the like B and C are the more easier ones. Is that
No.
what it is?
So,
Okay, no.
so say you want to take you want to demonstrate to me that you've mastered the ideas in learning target L2 for limits. So you'll
Okay.
go take a quiz. And so the first one, your first attempt should be L2A. So the letter denotes the order in which you should attempt them. And it really doesn't matter. You could bounce around, but for the sake of your sanity and keeping track of things, it's probably best just to go A, B, and C. That's all they mean. It just means that they're different. They're not a level of
All
difficulty.
right.
They're just different. And I recommend that you
Okay.
go A,
Yeah.
B, and C. That's all.
Sure. All right.
Okay.
Thank you.
You bet.
Yeah.
Any other questions? So remember, your grade in this course is largely based on how many learning target quizzes you take and successfully show me you've mastered the objectives of that learning target, right? Your job is to show me evidence that you understand the stuff, and how many learning targets you demonstrate mastery on, that's determines the grade that you get. Those targets are set out, or those goals, those numerical goals are set out in the syllabus. There's core learning targets, there's optional learning targets, and there's these other learning targets called mathematical practices that we haven't really talked about yet, but we're getting to the point where we can start doing some of those. So if you're curious or you don't remember how learning targets and the number that you pass relate to the grade you get in the class, go and look at the syllabus. It's in there, and those numbers are in there. And depending upon how things go in class for us, those numbers may or may not change, but I will guarantee you that they'll never go higher. Those numbers will never go up, right? Those, if anything, I'll revise those numbers down if we lose some time. And I'm not worried about revising those down or taking more time. If I get a sense from you all that you want to spend some more time on things, but it is hard for me to get a sense from you about whether or not I should speed up or slow down. And that's just by virtue of the Zoom environment, right? And the fact that my gallery view here is a bunch of tiles with names on them or pictures on them. So if don't hesitate. If you want me to do another example, or you want me to explain something again or differently, or it raises a question, don't hesitate to ask, because in this environment, in this Zoom environment, that's even more important that people speak up or they chat out and let me know that they want some more clarification. All right, so before I start talking about newish stuff, let me just say a thing about the learning targets that we've been talking about. So the learning target we've been talking about most recently is learning target D2. Okay, and I went back and I looked at our syllabus, and there are three objectives, three outcomes in D2, and I'm going to write them down now. One objective is called the tangent problem, understanding the tangent problem, and I haven't said much about that. You probably read about it, but I'll talk about it today. The other outcome is finding the equation of a tangent line. And we've been talking about that. So check that off. And then the third objective is what's called the limit definition of the derivative. And that's where I ended last time. And I'll say something more about that today. So we've talked about about half the stuff we need for learning target D2. So you're in a good position. By the end of today, you'll have everything covered for D2. D3, I'm going to write down 3 or 4 objectives for that. 4 actually. So the first objective is understanding the derivative as a function in its own right. The second objective is understanding differentiability. When is a function, when can you take the derivative of a function? third objective is sketching the derivative of a function if you have the graph of the function. Let me write this slightly differently. Sketch f prime from a graph of, graph of f. So if I give you a graph of a function f, be able to sketch f prime. And then the fourth objective relates to the second one. It's the geometry of differentiability. How can you look at the graph of a function and tell where it's differentiable and where it's not differentiable? And while I'm doing this, let me just tell you what D4 is. D4, I'm just writing this. D4 concerns the rules for differentiation. And these are like the constant rule, the constant multiple rule, the sum or difference rule, the product rule, and I know I'm getting close to the bottom here, so forgive me. You can just grab these on when I post them. The quotient rule and the chain rule. So these are rules that help us calculate a derivative. So if somebody gives us a symbolic definition of a function, we can use these rules to calculate the derivative symbolically. And since I don't have room below, I'm going to put this above. And D4, also wants you to think of these rules as theorems. Okay, they have proofs, and so we'll talk about those briefly. But today, I'm going to finish up talking about D2 and work our way into D3, and we won't be able to talk about D4 until next time. Okay, so this is where we are in learning targets. You have everything you need to do to take those learning targets for the limits, the L area learning targets. Once we finish today, you'll have everything you need to do to go do practice problems and prepare for learning targets of areas D2 and D3. Any questions about this?
I have a question about the material in the quiz, but are we going to have a midterm?
Nope, it's all learning target quizzes. I mean, it's possible I could. I mean, so one of the principles of mastery grading is you want to give students all kinds of opportunities to demonstrate mastery. And so I could write up a midterm that would have a bunch of problems from a bunch of different learning target quizzes. And, but honestly, I don't feel the need to do that. I don't know that there's any more benefit in doing that than continuing doing learning target quizzes. So I do not have a midterm on our calendar right now. I'm happy just having you guys take these learning target quizzes. Does that answer the question?
Yeah, it does.
Okay. You know, and we don't need the pressure of these big midterm exams either, right? I don't need to put more pressure on you. I mean, this is enough pressure. This is a lot of stuff to learn. So that's where I'm coming from on this. Okay, so let's talk about math. And here, give me a second here while I organize my notes. I think they got out of order from this morning. I want to start talking about the tangent problem, which has a strong historical flavor. And yeah, so that's where I want to start. Oh, and so I'm going to show you a picture here. So let me change what I share. I'll stop sharing so you can see a picture. I'm going to hold up a book title to the camera. Okay, so here's the title of the book. You see that title? It's called The Calculus Wars, right? This is not a science fiction book, though I do like science fiction. This is a historical book. it might seem like that's an kind of a dramatic title, but this is a dramatic story. This is a real dramatic piece of history in mathematics. So this title here, right, says the Calculus Wars, and then it's kind of got some mathematical symbols there. Like in parentheses, there are pictures of two white European guys. The guy on my right is Sir Isaac Newton. He was from Great Britain. And the guy on my left is, let's see, Gottfried Wilhelm Leibniz. I always forget his first name. Newton and Leibniz. And so the mathematical notation here says they are not equal, right? And so that was kind of the basis of these calculus wars. So Newton and Leibniz are the two people that get credit for discovering the calculus, right? And that's what we're studying this semester. And the calculus transformed human society, transformed science and technology and the way people think. And even back in the days of Newton and Leibniz, people understood this was huge. And so there was lots of prestige associated with inventing the calculus. And so Newton and Leibniz were really kind of trying to position themselves as the inventor, the person to get credit. So historical hindsight tells us that both of them deserve credit. But Newton was a real jerk. And he did not play nicely. And so that's why this conflict is described as a war. And it's a fun thing to read about. And so I'd recommend this book. But this is what I want to talk about a little bit today, is where calculus came from. So I'm going to share my iPad again. So, and we'll talk about this in the context of the tangent problem. So let me tell you what the tangent problem is, and then I'll tell you a little bit more about history here. So the tangent problem is this. Given a curve in the plane, find the equation of the tangent line to the curve at a point. Okay, this is the tangent line. This is the tangent problem. And, you know, you should not be impressed with this problem because we solved it last time. We know how to do this. We know how to solve this. But back when Newton and Leibniz were alive, so when was that? That was like the late, well, we'll say the mid 1600s. We had, I'm going to write down their full name, Isaac Newton in Great Britain. And we had Gottfried Wilhelm Leibniz in what is now known as Germany, but then it was more complicated. Well, back at this time, this tangent problem was hard. And there were several things that made it difficult, and I'll talk about them a little bit. Tangent problem was hard. Some things that made it hard is they did not have the modern concept of function. Okay, so your understanding of what a function is deeper and richer than the concept that Newton and Leibniz had and their contemporaries had. Right? They did not have such an abstract view of function. Algebra was relatively new. Okay, and symbolic functions, oops, let me be more legible. Symbolic functions were largely limited to polynomials. Okay, and probably simple polynomials. Okay, they had other kinds of functions that they could talk about and they could describe, but they rarely wrote them down symbolically. Most functions were described verbally. And you can think of some of the functions or the curves that they were interested in were those that related to physics. Think of them as relating to physics, curves that are created like catenary curves, the curve traced out by a wire when you hang it between 2 points, right? That catenary curve, they didn't have an algebraic description for what that curve looked like, but they could describe what it was physically. And that physical description was what we would call a verbal definition of the function. So another thing that was going on is that until Newton and Leibniz, solutions to the tangent problem were case by case. Okay, what that means is each solution took advantage of some property of the function that was given. And I'll give you an example of how that might have worked, just so you have a feeling for it. But before I turn the page, I'll just say Newton and Leibniz, their solution they came up with didn't depend upon the function properties. It worked for every function. And that was a huge breakthrough. And that's what made a splash. Their approach was so generic that it applied in every case and solved every case that had a solution. And it was remarkable. And that really made the mathematics community in the mid 17th century stand up and take notice of these two people. So here's an example of a function and how we can solve the tangent problem using properties of the function. So the function I want to use here is a function that gives us the semicircle. Okay, so you can say this is a semicircle of radius r. So the modern way we would describe this is it's the semicircular arc that goes to the point r comma 0, centered at the origin. Okay. So suppose you want to solve the tangent problem at that point that I just marked. So we want to draw the tangent line there. So how would people in the 17th century have solved this without Newton and Leibniz's approach? Well, they probably would have done something like this. They would have said, okay, let's take the center of the circle and take this point of tangency, and let's draw the ray that goes through them. And we call this a radial line because it follows a radius. And then they would say, it's well known that the perpendicular to a radial line is tangent to the circle. And so all we need to do is find that perpendicular at that point of tangency. And then we've got a tangent line. Ta-da! Tangent is perpendicular to radial line. Okay, so that's how they would solve it. So this would be an easy curve for people to solve the tangent problem for. A harder curve might be a parabola. How do you use properties of a parabola to find a tangent line? Well, there they would have used probably properties of conic sections and constructive techniques with straight edges and protractors and stuff to find a tangent line. Okay, so that's an example of using a special property of a special curve to solve the tangent problem. But Newton and Leibniz had their general solution that always worked. Okay, and it was based on the idea that if you've got a curve and you want to know what the equation of the tangent line is, so here at some point x naught, they said, well, look at another point on the curve, and you can always find the equation of the secant line. So the slope of the secant line is the rise over run here, created of the triangle, or yeah, between these 2 points. And Newton and Leibniz, introducing this idea of limit, said if you take that point and you move it down the curve by taking h smaller and smaller, the tangent line will tilt. And the closer your point gets to, the closer your other point gets to your original point of tangency, the closer the secant line will become to the tangent line you seek. And so the slope of the secant line is getting closer and closer to the slope of the tangent line. And so their observation and their assertion was the slope of the tangent line is the limit of the slope of the secant lines. And so their contribution to mathematics and human history is this idea of the limit, okay, which was really deep and transformational. So this is kind of where we are right now. We've talked about everything that gets to this point of understanding and appreciating Newton and Leibniz's solution and how general it is. So today we're going to start digging deeper into what this means and how do we interpret it. Are there any questions before I say more? We good? Yanni's giving me the thumbs up.
Dr. Miller,
Yes.
Talk about what tipped them off to even begin in this direction of thinking.
Can you? I missed the first 2 words of your question.
Sorry.
Sorry.
Does the book ever discuss what tipped them off into like start steering them to this direction of thinking? Like what made them start to like apply these things?
Yeah, no, that's a great question. What I'm going to write this down. Just whatever made Newton and Leibniz think about these things. Okay, so let me say a couple of things about it because I think it's historically interesting. So Leibniz, so he was in what we now call Germany, and he was a philosopher. And one of the things he spent a lot of time thinking about were these things called infinitesimals. Okay, things that were smaller than anything else that had a length, but they weren't zero. And he thought that they were a really powerful way to understand the world around us, and from a physical perspective and from a philosophical perspective. And that line of thought and that line of thinking led him to, you can probably appreciate, that it relates to this idea of the limit of something going to zero. So that's what Leibniz was doing, that led him to be thinking about this stuff in mathematics. And Leibniz didn't grow up as a mathematician. He didn't grow up as a scientist. I think he grew up kind of as a lawyer, and he learned mathematics a little bit later. I think that's right. Learned mathematics and philosophy a little bit later. Is that right? I think that's right. Newton, on the other hand, so this is kind of germane to us today, right? So he lived in Great Britain. And he was always a genius. And he was recognized as a genius from a young age. And he went to all these good schools, even though he was born of a modest means, but he was always a thinker, always in math, always in physics. Okay, and he was a big thinker. And he was not a people person. And so he spent a lot of time alone. And in fact, so let's go look at something. I want to look for this with you. So let me share a browser with you. When was the Black Plague in Europe? Is that right? Is it the Black Plague? Not the Black Plague.
Are you thinking of the Enlightenment?
No, there was a pandemic back.
You mean the bubonic plague?
Yeah. Bubonic. I think that's right, because
the bubonic plague would have also been called the Black Death because of some of its effects and how it caused flesh decay. There could be cholera, the syphilis outbreak. Europe just had a whole bunch of things going on.
Yeah. So here these searches for Black Death, they all come up mid 14th century. But what was the plague that was in the 17th century?
Maybe you can look that up. Plague in 17th century. Europe.
I think it's cholera.
The
Great Plague was spread by Black Death bacteria that lay dormant for 300. Anyway, okay, so here we go. There is the second plague epidemic in Europe in the 17th century. So this was right when Newton and Leibniz were alive. So the parallels to today are not overlooked. What Newton did is, instead of hanging around in London, where the plague was ravaging the city, he decided to flee the plague, and go back to his family home in rural London or rural England. I forget where it is. And he spent years there just thinking. And that's when the calculus was born. He wrote the Principia Mathematica there, which is a treatise on the way the universe works. And so you've got Newton's laws of gravity come out of that time. It was a very intellectually productive time for him while he was fleeing the plague. So he was thinking about these things he called fluents and fluxions. Okay. So they have some relationship to this limit as h goes to 0 too. And so his thinking at that time leads to the calculus, much like Leibniz's thinking on infinitesimals lead to the calculus. So one of the points I want to make here is Newton was a very poor communicator. Okay, his ideas were very hard to understand, and Newton would not share his ideas for fear that other people would steal them and take credit for them. So Newton's ideas did not get passed around very quickly or very effectively, whereas Leibniz was very well liked. So we'll use it. He was a clear communicator. And he invented, and you're going to think I'm a huge nerd by saying this, okay? I recognize that, but I'm unapologetic. He invented great mathematical notation. Okay? It's so good we still use it. It's called Leibniz notation. It's not good for everything, but it's really good for some things, and I'll introduce those to you maybe next week. So this made it easier for Leibniz ideas to spread. This made it harder for Newton's ideas to spread. Okay, but also, yeah.
Leibniz like ideas also been easily spread because of the invention of the printing press in Germany.
Yeah, I think that's a good point too. That the printing press and the rise of book manufacturing helped that. But I think books were distributed mainly between like universities and things. It's not like people were reading novels, but that certainly helped the spread of the ideas. It also helped Newton's ideas spread as well. Having your work published in books and published in journals was a really big deal back then. So, and sending letters and spreading your ideas through letters was a very big deal back then. But one thing that really worked to Newton's disadvantage was his geography. So let's look at one more, something up here. I'm going to go back to a browser. So let's look at a map of Europe. Find a good map of Europe. Will this get big enough? So here's a nice map of Europe. So you don't need to see this in detail, but right here are the British Isles. Okay, so Newton was hanging out here when he was doing his work. And Germany is right here. And, I think that Leibniz in his life, he was moving around between places now called Germany and called France. But we say that Germany is on the continent, it's on the European continent, and Great Britain is not. And so this water, right, the fact that Great Britain was isolated from the continent really was made it harder for Newton to get his ideas and spread. And it made it easier for Leibniz's ideas to spread. Right? So Leibniz had a bunch of stuff going for him that Newton did not. Right? Nice guy, good communicator, on the continent with everybody else who's interested in this math stuff. Yeah, and not a jerk. So this is just some historical context that's kind of interesting. None of it changes the fact that both of them invented this stuff independently from one another. It's kind of remarkable the way that happens, but this is kind of a lesson in the history of science that inventions sometimes happen independently, kind of at the same time. It's almost like society or culture is ready for something to be invented. And it doesn't change the fact that the ideas were hugely important and they really transformed the way we think of technology and science and even society. Yeah, so that's what I'll say about Newton and Leibniz and the history and where this stuff comes from. I think the question about what made them even think of these things is a good question. And that makes the history kind of fun to read. But I'm going to go back and I'm going to say, just remind us that this was their solution to the tangent problem. Okay, this is using modern notation. They did not have the formal definition of limit. Leibniz talked in terms of infinitesimals. Newton talked in terms of fluxions and fluents. This is the modern notation for it. And this is the notation that we'll stick to. But this is their solution. So let's explore this a little bit more. Let's solve the tangent problem in the way Newton and Leibniz would have solved it. Let's calculate the tangent line to the curve y equals 1 over x at x equals 1. So I'm going to do this once and lay out all the steps, and then we'll do another example, and then I'll ask for your assistance, and you'll just throw stuff into chat or you'll vocalize it. So I'm going to start out by putting this little symbol here saying this is scratch work, so I don't want anybody else looking at it, and I'm giving myself permission to make mistakes. So scratch work, we want to look for the target, the tangent line. So the first thing I'm going to do for myself is write down the point slope form for the tangent line. And I'm going to use the point slope because I'm given the x coordinate of the point of tangency. And since I know the relationship between x and y on the curve, I can figure out the y coordinate of the point of tangency. So I'm going to do that next. X naught is 1, and y naught is 1 over x naught. So that's 1 over 1 is 1. So I know this about my tangent line. And that tells me the only thing I have to compute now is m, the slope of the tangent line. So I'm going to use Newton and Leibniz's idea that the slope of the tangent line, and I'm going to denote it m sub tan, is the limit as h goes to 0. And here I'm going to write it in the generic way with the function name, understanding that up here, this is telling me f of x is 1 over x. All right, so I've just written down the limit definition of the slope of a tangent line. So what do I do next? Well, the next thing I'm going to do is whenever I divide by a number, that's the same thing as multiplying by its reciprocal. So I'm going to rewrite that division as multiplication. And then I'm going to use the definition of my function. So f of x naught plus h is 1 over the quantity x naught plus h. And f of x naught is the quantity 1 over x naught. And next I'm going to plug in x naught, since I know that's 1. Okay, so I've got this algebraic expression here involving h's. I would like to use naive evaluation of a limit if I can. So let me try. But if I try, immediately I see here, if I plug in 0 for h, I get 1 over 0, which is undefined. It doesn't make any sense. So I just have to stop. I can't do naive evaluation. But then what can I do? Well, let's look at the other term here. This is the difference of two fractions. So maybe I'll simplify and get rid of that minus sign. So I'll, instead of writing this as the difference of two fractions, I'll write it as a single fraction. So that means I need to find a common denominator. And that's pretty easy in this case. I can multiply the top and the bottom here by 1 plus h. So I get the limit as h goes to 0 of 1 over h. All right, and now I'll simplify that difference of two fractions. I get 1 minus 1 plus h in the numerator and 1 plus h in the denominator. And then you'll notice that distributing this minus sign, I get 1 minus h. And so those ones cancel out. So I'm left with 1 over h times the quantity h over 1 plus h. And that makes me happy because this h down here that had been causing me some problems from a naive evaluation standpoint cancels with this H up there. That's right.
Dr. Miller,
Yeah.
if you're distributing that minus sign, wouldn't it be negative H in the numerator?
Thanks, man. Very important. Yep. So that means I'm left with this. And now I can use naive evaluation. I can plug in H equals 0 and I get minus 1 over 1, which is just minus 1. So that allows me to conclude that my tangent line has that formula. Okay. All right. So now I'm thinking back to when I was a student of math. I always liked to have a way I could check my work. So how could we check this work? How could we make sure that this formula is right? If anybody has an idea, they can vocalize it or throw it in the chat. Anybody?
Could you repeat the question again, Doctor?
Yeah. So here we calculated that this is the formula for the tangent line. How can I check to see if it's right? Anybody have any ideas for that? So
Yeah,
Yanni,
I also thought might work.
what's that? Put in another value?
Yeah.
Yeah, so the problem with that, so I'm going to copy this over to the next page. So we've got this. I could let's see, let's clean it up a little bit. So it looks like we could write it as y equals 2 minus x. So what value could I plug in to help me verify that it's correct? We know it goes through the point 1, 1, because we built it to do that. So we could just double check. Let's plug in x equals 1. And sure enough, I get out y equals 1. So I guess that's a good thing to check to see if I did any algebra errors, but this shouldn't come out as a surprise because you can just see that from this formula right here. What other input could I put in to check? The silence is correct. There is no other input you could put in to double check it, right? So that's not going to be a good method. Anybody else have any thoughts about how I could check to see this, if this indeed was the graph of the tangent line?
You could just graph 1 over x and then graph the tangent line.
Yeah,
See
exactly.
if they line up.
Exactly. That's exactly what we would do. And, Newton and Leibniz couldn't do that. So let's go to my favorite. I'm now sharing my browser with you. I'm going to take you to Wolfram Alpha, my favorite tool to plot things online. So we're going to plot 1 over x and 2 minus x on the interval from 0.5 to 1.5. So that interval has x equals 1 right in the middle. And the x's don't go so small to get involved in the vertical asymptote here of 1 over x. So let's see what Wolfram Alpha tells us. So it gets the formulas right. And there we go. There's the picture. So how does that make you feel? Good? Bad? Confused? Giovanni's got his thumbs up in the gallery.
This is what we wanted, right?
Elizabeth, this is what we wanted, is it?
No, is it? That's what I'm asking. Is it?
Yeah, that's a good question. Is this what we wanted to see? Does this look like a tangent line? At x equals 1, so here I've got my crosshairs lined up at the coordinates 1.1. Okay, throw it in the chat. Here's a 3, 2, 1 exercise. Is this what we wanted to see? Does this show us that our work was correct? Yes or no? 5, 4, 3, 2, 1, go. Yep, you're right. This is good news for us. This shows us that our work was right. Does this purple line look like a tangent line? Absolutely. It intersects the graph at one point. Looks like it's kissing it at that point, staying on one side. It's got all these properties we expect a tangent line to have. We don't require them to have all of them, but those are the ones we look for. Absolutely, this looks good. So we should be happy looking at it. Good, Elizabeth? Good. There comes a point in mathematics where you have to follow your gut, right? You got to train your gut. And the way we train our gut, and this is all new, so you don't have anything to base this on. You train your gut through analogies, right? Some ideas that you understand really well, and hopefully they inform other new ideas that are more complex. We talked about drawing tangent lines, what it looks like to draw tangent lines, or how to draw a good tangent line. And that should start feeding your gut to give you an idea of what a good tangent line is. And hopefully that informed this gut reaction that a lot of people seem to have in the chat that, yeah, this looks right. This is a tangent line. Is this a proof that this is a tangent line? No, this is not a proof. This is just evidence that we were right. The real proof is back in our work. I'm going to go back to my iPad. Yep, and it went to sleep, waking it up. The real proof is right here. Okay? Doing these computations and doing them correctly, this is the proof that that's the tangent line, because Newton and Leibniz told us it was the tangent line, right? All we were doing basically in plotting was just making sure we didn't make a stupid error, right? If we'd seen like it, here, let's go back. Oh, and we need to take a break too. Let's go back here and suppose that I was a little bit wrong. Suppose that we were plotting 0.9, okay? Slightly off on the slope. We get a line that looks like this, okay? That's clearly not a tangent line. It's certainly not tangent at this point, okay? So if that had been our answer and we looked at this graph, we'd say, oh crap, we did something wrong. And this would be information to tell us to go back to our work and say, come on, Zoom. Tell us, oh, we've got a mistake here somewhere. We got to go find it. But it turns out when we plotted this, the plot told us, hey, you're right on. And so we can have confidence that our work here was good. So it's kind of a lesson that as a student of mathematics, it's always good to have a couple different ways to look at a problem. And here we did it. Had a symbolic way to look at it. Then we had a graphical way to look at it, compare the two, and they reaffirmed the work of each other, and we move on with confidence. All right, so I'm sorry, it's 11 o'clock. I'm 10 minutes over on a break. Does anybody want a break? Nobody wants a break?
I'd like a break.
Yes, this is the response I was expecting people to have. All right, so let's take a 5-minute break. And I'll put my music back on and we'll pick up where we're leaving off here. Okay. Any questions before I start working on another example and asking for your help? We good? Okay, so before I proceed, let me sort of give you a piece of advice. You can practice the stuff that we're talking about with functions that like any quadratic function. So pick a number capital A, pick a number capital B, pick a number capital C. And you can calculate the slope of a tangent line at any input that you want. Okay, using the Newton and Leibniz approach, you can do this, and then plot the result after your computations and see if it's right. So this is good practice for figuring out how this all works. I'll just point out that if you have A equals 0, then you're just going to have a line, and I'll do an example of a line in a minute. So really choose an A that's not equal to 0, and then, dealer's choice for what you choose your B's and C's to be. Okay, so here's an example of how you can practice if you're sitting around watching TV or something. Though this probably takes more concentration than you can do multitasking. This is not a multitasking practice. All right, let's do another example. So I want to do this function. Let's look at the graph of x squared, so the graph of the squaring function. And let's look at it at the input -2. And so what's the tangent line at x equals -2? And so when x is -2, y, if you plug in x in here for -2, you get about 4. So what's the tangent line at the point -2, 4? Okay. So here, let's do some scratch work. So here's an equation for a tangent line, or for a line. Here's another equation for a line. So here's a 3, 2, 1, go question for everyone. Which form of line do we want to use? A or B? Pick one, type it into the chat. I'll give you a countdown and we'll all share. Which we want to find a tangent line. So which of these two equations do we use to start with? A or B? 5, 4, 3, 2, 1, go. All right, thank you for playing. The answer is A. We use this form. Anybody want to throw into chat or vocalize why this one is better for us than this one?
In kind of form B of the equation, you have to calculate both M and V, whereas in form A, you don't. You only have to calculate M because you can just kind of plug in X naught to find Y naught.
Yeah, exactly. Very good, Cyrus. In both of these forms, the point slope form and the slope intercept form, M is a mystery. That's what we're looking for M. But in the slope intercept form, we don't know what B is. Whereas in the point slope form, we do know what X naught and Y naught are. Right? They're right here. So A is easier. Okay, that's why we choose A. Mathematicians are the laziest academics around because they always want to do something as easily as possible. They don't want to mess with something that's more difficult than it has to be. So we always want to take that route of least resistance. This one is the route of least resistance because the only thing we don't know is M, as opposed to here, there's two things we don't know. All right, so point slope, it's our favorite form for a line. So we need to find M, slope of the tangent line at x equals -2. And Newton and Leibniz told us here's the general form for it. So in the next two steps, I'm going to specify what our x naught is, and then I'll use our formula for F. So first, let me specify x naught. It doesn't matter what order you do this in. Last time I did the function. This time I'm doing the input. And the next step here, I'm going to use the function. And I'm also going to pull this h in the denominator out. So our function is the squaring function. So I get that. So let me square things out in the next step, and I'm going to give myself a little bit more room. I'm conscious that I'm close to the bottom of the screen, so I don't want to create problems for people. So this is 4 minus 4h plus h squared minus 4. So one thing I'll point out in the previous step, you get to this step and you say, okay, maybe I can do naive evaluation. But when you do that, you see this first term, you think I've got division by 0. Oh, that's no good. I've got a finite number in the top, 0 in the bottom. That's bad. Okay. So you just put that off and you go to the next step. And when we get here and we expand, you see I've got a -4 and a 4, and those cancel. And that's good news because it simplifies things. And then you see in the stuff that's remaining, each of these terms has an h in it. And so you can factor an h out. And so let's do that in the next step. And I'm going to copy this over to the next page. So we can see it. Let me get rid of this craziness. So 1 over h from previous. And then here I've got an h times -4 plus h. Written that way, you see, oh, cool, this 1 over h and this h, they cancel out. So I'll do that, cancel. And you're left with, and I'll rewrite this just for clarity. You're left with the limit as h goes to 0 of -4 plus h. And here's something where you can evaluate using naive evaluation, right? Plug that h equals 0 in, and you get -4. So this shows the slope of our tangent line is -4. So the equation of our line, if I remember this from the previous page, is y minus 4 equals -4 times x plus 2. Okay. So how could I check this to see if I'm on the right track? Yeah, Giovanni and Niani put into the chat and graph it. Use Desmos, Wolfram Alpha, graphing calculator, graphing function on your mobile phone, whatever. You can graph it and see. And that would be evidence that you did your calculations correct. And I'm pretty sure, I'm very certain, very confident that this is the correct formula. Let's do one more. Let's see how much time do we have left. It's 11:16, so we got a half hour left. Okay. So I'm going to do f of x equals mx plus b. All right, so this is going to be a generic line. Okay, this is a generic linear function. And I'm going to do it at a generic input. I'm not going to specify what that number is. Okay. Find the tangent line to the graph of f of x at x equals x naught. Okay, so let's see how this works. I've got a lot of abstract things happening here, and I just need to keep track of them. And you do everything as if these were a number, okay? Treat this as a number. Treat this as a number. It's a symbol, but it's taking the place of a number. And treat this as a number. The only thing that's not a number is this. This x is a variable, right? So treat these like they were numbers and you'll be fine. So how do we do this? The first thing we did was write down the equation of the tangent line. So how are these things different? So this x naught is that same x naught. So that's not going to change, right? We're going to keep that written in that same way. Okay? It's just an unknown. But what I can do is this y naught, right? It comes from the function. So I can write down y naught. It's always equal to f of x naught. But f is, we've got the formula. So I can plug that back in here. And so my formula for the line becomes y minus y naught, which is m x naught plus b, equals m times x minus x naught. Oh, but I need to be careful here, right? Anybody see what I need to make? I made a mistake, kind of. I set myself up for some pain. Anybody see it?
The x naught is on both sides of the equal sign.
That turns out that'll be okay. That's not a bad thing. That's okay. The mistake I made is in a different symbol. I've got that B, but that's okay because that B came from here. I was given that as part of my formula.
Is it the M?
What about the M could be a
Is it
problem.
the way you combine?
Can you say that again, Elizabeth?
I don't know. I just don't like the way they look.
You don't
I
like
just
the way
don't
they
like
look?
the way they look. One is combined with one.
Okay.
One is combined, and won't
so-
won't have to contribute to like.
Okay, so your gut intuition is good, and it's good to follow your gut. So let me show you what I did wrong, and it's an easy fix. So we were given this. So this is the formula for some line, okay? And then we created this, and in doing so, we accidentally recycled or reused the symbol M that had already been used in the problem. It's coincidental that the M in both cases stands for a slope, but we have no reason to believe that they're related. So I just have to find a different symbol for that M in my equation of the line. So what I'm going to do is I'm just going to call this M sub tan to remind us that it's the slope of a tangent line. Okay. Now by doing that, I no longer am reusing a symbol. I've got M up here by itself, and down here I've got a different symbol, M tangent. Okay. So let's see, what does that affect? Let me do this in red. So we have this M and this M. Okay. So this other M is from the function. It's only this M that I need to change to M tangent. So let's do that. Fix. Y minus mx naught plus b equals M tangent x minus x naught. So I'm going to have to copy this to the next page to continue our work. And erase stuff that came along for the ride. And that's a B, not a 6. So let's calculate M tangent. That's thanks to Newton and Leibniz. The limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. So I'm going to simplify this in two ways. One is by pulling that h out as a reciprocal. And then f of x naught, that's m times the input plus b. And f of x naught, well, rather, let me back up. F of x naught plus h is m times the input, x naught plus h, all plus b. And then f of x naught is m times x naught plus b. And what do I do next? Well, I can't do naive evaluation yet because I'll get 1 over 0, and that's not defined. So that means I should go simplify this stuff over here. And that's going to usually be the case. You're usually going to have to simplify the stuff before you deal with the division by h. So what do we get? The limit is h goes to 0 of 1 over h. So here we're distributing the stuff. We got mx naught plus mh plus b. And now distributing the minus sign, we get that. Now, if you've done stuff correctly, you'll get a bunch of cancellation here at this step. Whenever you do a derivative problem from first principles, and that's whenever we're doing a derivative problem using Newton and Leibniz's idea, we're doing it from what's called first principles, as opposed to using a theorem. I'll talk more about that later. But here, whenever you do something from first principles, you should get cancellation. So you've got a minus b and a plus b, so they cancel. And you also have a mx naught and an minus mx naught, and so those cancel. And so
Dr.
we're
Miller,
just,
would this be the same as doing difference
say again, you cut out on the last word.
quotients in the way that we start to
Yeah.
with the way that we cancel things out, would this be similar to difference quotients?
Yeah, and in fact, this is a difference quotient right here. That's exactly what we're doing. We're calculating the limit of a difference quotient. And so down here, we're simplifying the difference quotient in a way that helps us manage this potential division by 0. Does that answer your question? Good. All right, so we're left with an m times h here. And so this h will cancel with this h. And we'll be left with the limit as h goes to 0 of m. So we're left with an m. And so holy smokes, look at this. These are the same. So if I go back to my, oh, this is kind of low on the page. Let me redo this somewhere that's higher. I'll go over here. We conclude that our tangent line is, what did we say? Y minus, this is mx naught plus b equals m times x minus x naught, right? Where this use of an m is not a mistake, right? We show that the m tangent is actually the original m, right? And that's why we put that there. So this is the equation of our tangent line. Big deal, you say, Miller. Big deal, showing off all your ability to manipulate symbols. Well, watch this. If you start simplifying this business, you'll see we have a minus mx naught on both sides. So if you add mx naught to both sides, they cancel. And then I'm going to add b to both sides, and I end up with this. And I'm going to put a big exclamation point right there. Why did I put an exclamation point right there? Anybody want to tell me?
That was what we started with.
That's what we started with. The equation of our tangent line is exactly the same as the equation of our original line. And that's cool with a capital C, right? So what does that mean? That means this. I'm going to draw a picture. Somebody gives you a non-vertical line and asks you for the tangent line at some point on that non-vertical line. Well, what we just proved is the tangent line coincides with the original line. And so you can just give them back that formula for the tangent line. Another thing that this tells us, all tangent lines to a linear function have the same slope. So if I take a different input and I want the tangent line there, it's going to have the same slope as the previous calculation. Input here, tangent line there, same slope as the original function. Okay. So this is a really important idea, a really important example to understand. Okay. All right, it's 11:30. Let me double check something. Okay, so I'm going to go back some pages because I want to double check what the learning target said. All right, so here at the start of class today, I reviewed what the learning targets say in D2. We're talking about the tangent problem, done. Find the equation of a tangent line, done. Limit definition of the derivative. So what we've been doing is we've been computing the derivative of a function at a point. So I'll clarify this, but we're actually done with that. So next I want to move into D3, okay? And I think I'll be able to get through most of this in the next 20 minutes. So buckle your seatbelt. So I've mentioned this before. So this will look familiar. So if we have a function, if y equals f of x has the property, well, let's see, how do I want to say this? Say somebody gives you a function and an input that's in the domain of the function. We can define a new function that takes x naught and gives us the limit as h goes to 0 of f of x naught plus h minus f of x naught over h, right? The Newton-Leibniz idea. And we can call that value f prime of x naught if the limit exists. Okay. This new function f prime is called the derivative of f at x naught. Okay, so I've just defined the derivative function. You now know how to calculate these limits. It involves doing algebra a lot of the time. We can't do this this doesn't work for every function that we know of, and we're going to spend some time examining some other functions. But for polynomials, this will always work. And when this limit exists, we can define this new function called the derivative. So what I want to talk about now is, what does this mean? What, and how do we know if this limit exists? I'm going to turn the page now. So this is the topic of differentiability. When does that limit exist? So here's the definition. We say f of x is differentiable at x if this thing here that I'm defining, I just defined on the previous page, and I'm going to rewrite the definition here, so don't worry about that. If this thing, which is the limit as h goes to 0 of f of x plus h minus f of x all over h, exists and is finite. Okay, I don't want any infinite values for this limit. I want these limits to be finite. Okay. So this is what it means for a function to be differentiable at a point. So let me just rewrite that down here. Differentiability at a point. So we have another definition. If you think back to when we talked about continuity, we defined continuity in a similar way. We defined it first at a point, and then we defined it on an interval, and we did it just like this. We say f of x is differentiable on an interval AB in its domain if f of x is differentiable at every point in the interval AB. Okay, so this is the definition of differentiability on an interval. Okay, and it really depends on the definition of differentiability at a point. So what I want to talk about for a couple of minutes is, what does this mean? What does it mean for a function to be differentiable? And when I say meaning, I want you to think in analogy with the meaning of continuity. When we talked about continuity, what does it mean for a function to be continuous? You know, one of the things we said is, well, a function's continuous if we can graph it without lifting our pencil from the paper. Okay. I want us to come up with a similar way and an analogous way to understand differentiability. And I like to think of this as a geometric way of thinking about differentiability. How can we recognize, just by looking at a graph, if it's differentiable? So to start with that, let's consider this definition. So I'm just going to copy it over to get it out of the formal definition we wrote down. So what does it mean for this limit to exist? Well, my h is going to 0, so this thing down here is going to 0. So for this whole thing to exist, my numerator up here better not be going to some finite non-zero number. If this goes to some finite non-zero number, then this whole thing goes to infinity, and so the limit isn't going to be finite. Or maybe the whole thing doesn't go to a single number, and so the limit doesn't exist. So if on the basis of this condition, in this limit, my numerator here must be going to 0. Okay, so I'm going to write that down in English. From the definition, condition, the numerator must go to 0 in the limit. That means the limit as h goes to 0 of f of x plus h minus f of x equals 0. But by the limit laws, that means this. But what does that tell us about the function? Can anybody tell me what that tells us about f of x? Anybody? It's expressed in a slightly unusual way, but it's an idea that you've seen before. Nobody? Any guesses? This means f of x is... Nobody wants to guess? All right, here's an opportunity for people to be brave. We're going to play the 3-2-1 game. So if you have a guess, and guesses are free, they can be wrong. Doesn't matter to me. Just that you're participating is important. This means that f is blank at x. What goes in the blank? It's one word. I'll give you a hint. It's one word. I'll give you another hint. You want another hint before we play? Brianna wants a hint. Anybody else want a hint? If nobody else wants a hint, I'll text her privately. Here, I'll set up to text. Anybody else? Oh, Giovanni, I don't want to text two people privately. Anybody else want a hint? I could do two. Joseph? Okay. Here's the hint, since more than two people want it. The hint is the word begins with a C. Okay? So what word goes in there? We're going to play the 3-2-1 game. Take a second. Take a guess. No harm for getting it wrong. This means f of x is blank at x, where the word begins with a C. Single word. 3, 2, 1, go. Hey, that's great. I'm glad so many people guessed. And that you all guessed with C words. That's great. The answer is continuous. This is basically the definition of continuity. Okay? A function is continuous exactly when you can write something down like this. It's unusual that we don't usually write it using an H, but that's okay. This is the definition of continuity. Okay, so what does this mean for us? And we've got 10, 11 more minutes. I'm going to go to the next page because I've run out of room. This means, or this suggests, because it's not a proof, that if f of x is differentiable at x, then it is continuous. Okay, so this is something you need to know, that if f of x is differentiable at a point, then it must be continuous at that point. And in fact, this is a theorem. And I've got a screencast ready for you to watch on this theorem. I'll post it after class today. Okay. So the theorem is differentiability implies continuity. Okay. So that's for later. But this is something you just need to appreciate. If a function is differentiable, then it must be continuous. But as an immediate consequence of this theorem, and I should write this more legibly, it's a corollary. If f of x is not continuous at x equals c, well, we'll just say at x, then f of x is not differentiable at x. So this is the first way to recognize when a function is not or fails to be differentiable. If a function fails to be continuous, then you immediately conclude that it's not differentiable. Okay. So I could hold up a graph of a function right now, and if I asked you, where does this function fail to be differentiable? The first thing you look for are points of discontinuity, right? If there's a hole in a graph, if there's a point discontinuity, or if there's some sort of break, then you know the function's not differentiable there. Okay. Just from this kind of simple analysis of the definition of differentiability, it'll become clear to you in a second. And in fact, it's kind of obvious here. If somebody asked, what's the equation of the tangent line at this point? You'd look at them and say, hey, idiot, there is no tangent line there because there's no point of tangency. There's no place for it to be tangent to, right? And they'd be like, oh, okay, yeah, you're right. And they say, well, what about here? What's the equation of the tangent line there? And then you'd say, well, buddy, what tangent line are you talking about? There's no natural way to talk about a tangent line there. Okay, it just doesn't make any sense. and this is kind of hand wavy, so I'll make it more specific and make it more obvious to you that this is the case. But this is one way you could do it. You could say, how do you draw a tangent line? And you could do the same thing in this case here. Okay, so to try to understand on our road to understanding what it means, how can you look at a function's graph and determine if it's differentiable or not? This is kind of the first main result. Look for continuity. But there's more. It turns out, fact, differentiability needs more than continuity. God, differentiability needs more than continuity. When we write this down, when we want this limit to exist, right, it's got to exist from both sides, right? So your graph has to have the property that the slope of the secant lines from both directions approach the same thing. And one way that can fail to happen is, in a function that I call the cusp. It's one of my favorite functions. It's the function x equals 2/3. And its graph looks like this, like a bird beak. And it fails to be differentiable here at this point. Because if you look at the secant lines on one side, they all have positive slope. But if you look at the secant lines on the other side, they all have negative slope. And if you sort of make h get closer and closer to 0, those slopes only get bigger in size. So the slopes over here of these secant lines, they're going to positive infinity, and the slopes of the secant lines over here are going to negative infinity. And so this limit doesn't exist. Okay. So this is what's happening. This is one geometric way that you can fail to have a tangent line, is that these secant lines are doing something different. And the way we describe it in mathematics, it's the technical term, it's called pointy. Okay. What's happening here on the graph is that you have a sharp point on the graph, and that's prohibiting a tangent line from being drawn because it causes problems with these secant lines. So one way to think about this in the positive is that differentiability requires smoothness. For a graph to be differentiable, it's got to be nice and smooth. Can anybody think of an example of a graph that's nice and smooth? You can vocalize it or put it in the chat. Anybody? Graph that's nice and smooth everywhere?
Parabola.
Yeah, parabola, right? Y equals x squared. That's nice and smooth, got a nice curve to it. Yeah, Perkins, Stephen just threw in the chat the linear, right? Nice and straight. That's nice and smooth. You don't get smoother than straight, really. Yeah, because there's no changes. But yeah, parabola. Anybody else have an example of a function? Well, one more example that's nice and smooth. And by smooth, I mean no pointies, right? No sharp edges on it. Yeah, we don't have to be able to calculate the derivative, but in your knowledge of all the families of functions, families of elementary functions, can anybody give me one that's nice and smooth everywhere? X cubed, sure. Gabby and Giovanni, good. Somebody else. Stick your neck out. Is a sine function, is that nice and smooth? Cosine, Jay says, yep. Cosine is nice and smooth, so the sine must be nice and smooth. How about a logarithm? Is a logarithm smooth? Anybody? Giovanni gives a thumbs up. Anybody else got Giovanni's back? Elizabeth? Yeah, the graph of logarithm is really nice and smooth. How about an exponential? Yeah, yeah. Just about every function we know of, just about every one of the elementary function families we know of are nice and smooth. So this means, it sounds like maybe every function is differentiable. Can anybody give me an example of a function that's not smooth? No, we're not talking about vodka. Well, Elizabeth, cosine is nice and smooth. So Giovanni, I was making a joke. Can you? Sine is nice and smooth too. Giovanni, can you flesh that out a little bit more? What do you mean by absolute? Absolute what? Absolutely? Yeah, absolute value. The absolute value function is an example of a function that has a point on it. All right, and so I'm drawing in my iPad right now a cartoon of the absolute value of x. And it's got a pointy here at x equals 0. Okay, so the absolute value function is not differentiable at x equals 0. It's differentiable everywhere else because everywhere else it's nice and smooth, right? It's a straight line. But just right here, it has a little corner. It's not differentiable there. So I've got a screencast on absolute value and differentiability at 0 that I'll post and ask you to look at. Okay, so I really want you to be able to understand and explain and talk about why the absolute value function is not differentiable there. I want you to be able to talk about it in a very mathematical and precise way, not in this kind of, oh, it's pointy. That's a great way to talk about it once we've mastered the ideas, but there's the technical way to talk about why it's not differentiable there. So you'll watch the screencast and you can come with questions on Wednesday. But that's it. It's 11:50. Our time is up. I think I got through most of everything that I wanted to today. Next time, I'm going to go back to the first page of our notes today. Oh, yeah. So I did not get to talk about this, sketching the graph of a function if I give you the graph, or sketching the graph of a derivative if I give you the graph of a function. So we'll start there next time. But other than that, we got through everything we needed to do. So I want on that note, on the learning target quizzes, these sketching problems, I don't know how to solve this problem. But a lot of people are doing work for learning target quizzes on their own paper because it's hard to, for whatever reason. I don't care what the reason is. For me, it'd be hard to print a quiz out and then write on it and then upload it later. For problems like this, it's really pretty important that you work from a good representation of the graph that you're given. So I'm trying to figure out how to deal with that. But I wanted to let you know, in case you're choosing to do these learning target quizzes on your own paper, if you see a problem that's like this, you might want to approach it slightly differently from the way you've been doing it. I'm not exactly sure what that is, and we can have a conversation, and maybe some of you will come up with a good idea. So I'm open for thoughts, open for ideas. And that's where I'll leave it. Okay. So next time, starting here, and then we'll work into the D4 stuff, the rules, differentiation rules. All right. That's it. I'm done. Any comments or questions from folks before we close out the class?
I had a question.
Yeah.
For the tangent, when we're checking just to see if it's right on the graph, are we able to do that for the quiz or no? Because how would we check? Would we just be able to sketch it out ourselves?
So, yeah, what you could do on a quiz, right, is you could if you did it in Desmos, for example, you could take a screenshot and attach that to your PDF that you upload. Or, you could do that with Wolfram Alpha or whatever. You could take a screenshot or print the screen to a PDF or something. You can also do it by hand. By hand takes a lot of work. One of the benefits of doing using the technology is it's fast and easy. So I'd recommend taking a screenshot or something if you can. If you got questions about how to do that, let me know and we'll get you an answer. But does that speak to your question, Rihanna?
Yeah.
Okay.
Thank you.
Yep, good question. Anybody else? Okay, well, I will say au revoir, and I will see you Wednesday.
Have a good day, Professor.
Bye-bye. Thanks, man.
Thank you.
Thanks, everybody.
Thank you, Dr.
Thank you. Bye-bye.